All right, today is 24th of March, 2026. And in Chem 100, exam 5 on chapter 9 is due by midnight tonight. If you're taking it in Brightspace. We're going to introduce a new topic today, chapter 15 in your textbooks on solutions. And what you would be looking for in Brightspace is the slide set. PowerPoint slide set looks like this, right? And the review document that gives you problems to work in Brightspace looks like this. All right. And then if you get stuck, these are the worked problems that go along with that review document. Right. Okay. So let's take a look at solutions. We've learned how to, we've learned the alphabet. We've learned how to construct words or compounds, how to construct sentences, chemical reactions, how to balance those equations, how to use them to in a stoichiometry. Now we're going to focus in on stoichiometry with reference to solutions. And we'll stay confined to solutions that are in a water environment. These are the topics that we're going to cover. And first, what is a solution? We looked early on in the course at pure substances, right? Materials that cannot be reduced any further by chemical means. And a combination of those pure substances in which each substance retains its identity is a mixture, right? And one of those mixtures, the homogeneous mixture, is also called a solution. Some more terminology. All right. When you hear solvent, this is the one major component. Right? The one major component or pure substance in that mixture is the solvent. The solutes can be many minor components. Now, either one of these can be compounds or they can be elements. And we're going to talk about solutions. To begin with, we're going to introduce the topic of solutions with reference to any substance can be either a solvent or solute. And then we're going to focus, after that, we're going to focus on solutions where water is the solvent. That's the major component. Now, there are exceptions to that. Most notably, if you try to make a solution where start off with water and you put sucrose in it, right? Table sugar. Start putting sugar in there, dissolves, more sugar. Eventually, you reach a point where you've got equal amounts of sugar and water. And then you can just keep putting sugar in it and it'll still go into solution. So you end up with major component is sucrose or sugar, and the minor component is water. But we still call water the solvent, just to keep things simple, really. And because you would normally start with water and add sugar to it. All right. And we have remember one of the parenthetical additives we give to compounds or elements in a chemical equation. Remember, we could be either gas or a liquid or a solid. And then the other one that is common is AQ, aqueous. That simply means that the major component is water. All right, various types of solutions. Homogeneous mixtures. Can be made from, first example is gases. Both the solute and the solvent are gas phase. And I'm breathing a solution right now. It's primarily nitrogen, that would be the solvent, and oxygen would be one of the solutes. When you turn on if you have gas piped into your house from a trunk line, not from a tank of propane, but from a trunk line of natural gas, it's going to be a mixture of the major component, or the solvent's going to be methane. And minor components, at least one minor component is ethyl mercaptan. And we don't need to do the formula for that. Just know that ethyl mercaptan is what they add to natural gas to make it stink, right? Natural gas by itself has no odor. So if you have a leak, you don't even know it until it's too late. So we add this mercaptan, which is a sulfur-based compound that stinks really bad in very small amounts. So you can tell if you have a leak really easily. Once the solution is made, it is still a gas. Other solutions where the solvent is a liquid and the solute is a liquid, and the product, the solution itself is also a liquid, are things like antifreeze, right? Ethylene glycol would be the minor component, one of the solutes that we put in water in your radiator. And it, by another topic that we haven't covered, changes the boiling point of that water and the freezing point. So it keeps your engine from freezing in the winter when it sits idle, or from boiling over in the heat of the summer when it's trying to run at a certain temperature. Booze, right? Any type of alcoholic beverage is primarily water. And the other major, well, I wouldn't say major, the next most concentrated component is alcohol or ethanol. And then there's some other components in there also. Wines are also a solution primarily of water as the solvent and ethanol as one of the solutes. We can even have a solid solution. Brass is a perfect example of that, where you combine copper, that's the solvent, and then nickel is the solute. Now there can be some other things in there, but these are the major component, and the largest minor component is nickel. That's brass. Now you can't just put the two solids next to each other and make a solution. It doesn't work that way. You have to melt them, mix them thoroughly so that they're uniformly distributed, homogeneous mixture. Then when they cool and solidify, you have a solid solution. Carbonated water, right? Soda pop is primarily water, right? A liquid, and carbon dioxide, a gas. And when you dissolve the gas in the liquid, the product or the solution is a liquid with gas dissolved in it. The most commonly understood. The intuitive solution is one where you add a solid to the liquid and the solid dissolves in the liquid. Now you have a liquid, like salt water. Right? So you would have water again, but in this case, you would have sodium chloride. That would be the solute. And we mentioned one earlier, the sugar solution. Say if you make a solution for your bird feeder, your hummingbird feeder, you would typically use half and half, the same amount of water as you do sucrose. All right. Now, when the solid, in this case, we're going to focus on this one. When the solid is an ionic compound, you have, in the solid, you have an array of sodium and chloride, right? And it just goes on and on in 3 dimensions. But when you put it in solution, when you add it to water, water will pluck these ions off of the crystal and they go into solution. And in solution, you actually have the free ions, sodium ions and chloride ions. That's why water will not conduct electricity. But a salt solution like sodium chloride will conduct electricity because you have mobile ions to complete the circuit. So another point. In this case, if you have 1 mole of sodium chloride solid and you put it in solution, in the aqueous solution, now how many moles of solute do you have? You have 2 moles, right? 1 mole of sodium chloride makes 1 mole of sodium and 1 mole of chloride. So you have 2 moles of ions in solution. You get an interaction here. Water is a polar solvent. In other words, the water molecule is shaped like this, right? H2O. On this end of the molecule, it's slightly positive. It's not a complete charge. It's just that the electrons spend more time around the oxygen than they do around the hydrogen. So it gives this side a slightly positive charge, and this side a slightly negative charge. So when the water molecule approaches a crystal of sodium chloride, the negative side of the water molecule, right, is attracted to the sodium ions. And the other water molecules are out here, and they're pulling on this water molecule as it's attracted to this sodium. And as it starts to become dislodged, there's more room for other water molecules to come in. And eventually that sodium ion is pulled into solution and is surrounded by water molecules. That process is called hydration. A similar process happens for the chloride, but in this case, the hydrogen, right? Positive side of the water molecule is attracted to the chloride, and you get a similar effect in hydrating the chloride ions. This is typical of ionic compounds dissolved in a polar solvent like water. And that's an artist's depiction of sodium chloride going into solution. This will also happen when you try to put liquid ethanol into water and make some booze. Right? So with this water molecule, instead of the ionic compound like this, you'll have a molecule that is bound to these carbons like that, and like that, and hydrogen here, and then you'll have an oxygen and a hydrogen there. The difference in electronegativity, that is the ability of the atom in a covalent bond to pull electrons toward itself, the difference between the oxygen and the hydrogen is similar to that in water. So we get a slightly positive side here and a slightly negative side there. And the attraction then is between the negative of the water and the positive of the ethanol. And that makes ethanol soluble in aqueous solution. And any molecules that have these hydroxyl groups, we call them hydroxyls, OHs, attached to their structure, the more of those you have, the more opportunity you have to form these bonds, these temporary bonds between water and the molecule. So with sugar, sucrose, we have actually have two molecules. And we have an OH here. Oops. Yeah, that's right. And then an OH here, and then an OH here. This is glucose. I'm going to stop there. Sucrose, we just add a fructose molecule over here, and it's attached. It's called a disaccharide. It has two sugar groups to it. But the point is that these sugar molecules, all types of sugars, and there's a whole bunch of sugars that we could describe, have these OH groups all over the place. And what that does is it makes this type of bonding possible. This is called hydrogen bonding. It's a special type of dipole interaction. Well, there it is. There's sucrose. Okay, so this is the glucose part of the molecule over here, and then it's bound to this fructose molecule over here. And notice it's got all these hydroxyls scattered all over the molecule, which makes opportunities for bonding with water. Okay. Now the flip side of that is the inability of polar solvents to dissolve non-polar molecules. So the polar solvent in this case would be water, and oil would be the, it's not really a solute because it won't dissolve in water, right? It's insoluble in water because there's no place for the water to attack the molecules of oil to get them into solution. Right? So when we say a polar solvent and a non-polar solute, right? They will not mix. And that also brings up, let's see, I'm wondering if I have a comment on that already. when we say like dissolves like, what we're saying is that polar solvents readily dissolve polar solutes, and nonpolar solvents readily dissolve nonpolar solutes. So that oil will readily dissolve something like gasoline, which is itself a mixture, but octane is the molecule in gasoline that we're interested in. It will readily dissolve in oil because the oil and the octane are both nonpolar. Now here's a model which attempts to describe how substances dissolve in one another. Let's put it this way. Say you have a solvent and a solute. Okay? And down here you have the solution. Right? So what must happen? We take this in 3 steps. Okay? The first step, we have to add energy to separate solvent molecules. Okay? Sometimes we call that make a hole. Some place for the solute to go. Separate those molecules so you can stick a solute in there. In order to do that, we have to add energy. That's called an endothermic process. Similarly, we've got to get the solute molecules separated from each other so that they can go into those holes. So again, we have to add energy. This is also endothermic. Right? Endo means into, thermic means heat. So we put heat into the substance to separate solute molecules. Okay? Now that they're separated, we've got a hole and we've got separate molecules, we can put them together. Right? They can go into this solution. Right? And when they come together, they start forming these temporary bonds. And that gives up energy. We're taking them down to a lower energy state by combining them, and they give up energy. So this process is exothermic. Right? And we form bonds. Okay? Now let's see if that's what we're saying here. I mentioned that earlier, like dissolves like. Okay, so now that we understand that like dissolves like, which of the following solutes will generally not dissolve in a specific solvent? Okay, will carbon tetrachloride mix with water? In order to answer that question, we have to know something about the molecule. Right? We know water already is a polar solvent. Water is like this. right? How about carbon tetrachloride? Carbon tetrachloride is like this. And then toward the back is another chlorine. It forms a perfect tetrahedron. Now, it's true that the chlorine wants to draw electrons away from the carbon. So we say it has a dipole moment. It draws electrons this way, and this way, and this way, and this way. But what we have is a balance of pulls. The electrons are being pulled equally in all directions, right? So the dipole that would form in this molecule is canceled out. So overall, this is a non-polar molecule, right? So it's not likely to dissolve in water. Right? So that one will not dissolve in water. How about the next one? Ammonia. We have to know something about ammonia's structure. Ammonia is shaped like this. It's got those extra pair of electrons up here, which gives it that negative side. Right? So ammonia will dissolve in water. How about CH3OH? Right? There you go. You've got this negative here and this positive there. Methanol, which is also called wood alcohol. That's the alcohol that'll make you go blind if you drink it. Will readily dissolve in water because it is polar. And N2 mixed with methane, right? We're kind of switching gears here. N2 and methane. They are both nonpolar molecules. But it's an interesting thing about gases. Gases have so much room, so much space between the molecules that you can put anything into them. Any gas will go into any other gas. They are infinitely miscible, they say. So even if these are nonpolar or polar, it doesn't matter. They will dissolve in one another because they are gases. Right, so the only one that will not dissolve is carbon tetrachloride in water. Carbon tetrachloride used to be used as a dry cleaning agent until workers started to get sick, cancers and all kinds of stuff. And it was determined that carbon tetrachloride was not a nice chemical to work with. So the OSHA, the EPA got together and they banned it. So now we have to use something else that's not quite as toxic, but more expensive. Okay. So one of the characteristics of solutions I mentioned earlier is that the individual solvent and solutes retain their identity. We just mix them together, which also introduces the next characteristic of a solution. It has variable composition. That is, the concentration of the solute in the solvent is not fixed. Right? It can be anything within limits. So what we need to do is develop a way to express what is the concentration of any solute in the solvent. And one of the first characteristics of a solution we identify is what is the maximum amount of a solute that we can put into a solution. We call that solubility. What is the solubility of a solute in a solvent? And the first approach is semi-quantitative. In other words, what's the maximum amount? What do we have when we put all the solute into a solvent that it will hold? And it won't hold anymore. We call that a saturated solution. It's easy to make saturated solutions. You can even make a saturated solution of table salt and water. One of the ways to do it is, since most solids are more soluble in the solvent if you heat the solvent up. So we heat up our water, right? Put it on a hot plate and heat it up. That delta means heat. Heat it up, okay? Then we put a certain amount of sodium chloride in there. And it all goes into solution. And we make sure we look up in our chemical reference table, what is the solubility of salt? So many grams of sodium chloride per 100 milliliters of water. And then we take that amount and we add more to it. Then we put that in, we heat the water up because solubility is temperature dependent. We heat it up and we put it all in there. Goes into solution. And then we take this off of the heat. Now we have water and sodium chloride in solution. And we let it cool. Okay? As it cools, the excess sodium chloride will drop out of solution as a solid. And at room temperature, we will have solid sodium chloride on the bottom. Under those conditions, now we know that that solution is saturated. It can't hold anymore because whatever excess we had in solution is now precipitated at the bottom. That's the easiest way to make a saturated solution. Now, it's possible unsaturated is anything less than that. Concentration of the solute that's less than saturation is unsaturated. There's one other possibility. If we're very careful, we don't disturb the solution, right? We cover it and let it sit. Sometimes that solid will not come out of solution. It is supersaturated. All we have to do is disturb it. Say we could stir it, or we could scratch the inside of the glass, or we could just add a small crystal of sodium chloride to that solution, and the excess will now drop out of solution. And needless to say, these supersaturated solutions are very unstable. All right. Solutions are mixtures. So we need to find a way to express the concentration of solutes in the solvents. That's so that we can work with qualitative stoichiometries when we're starting to deal with reactions. Now, this unsaturated situation that we mentioned earlier can also be subdivided into a concentrated, in which large amounts of the solute are there, approaching saturation, and then dilute are those in which very small amounts of the solute are present. This is one of the first ways that we learn to express concentration. It's called mass percent. The hazard with using percent as an expression of concentration is that percent is a dimensionless number. What does that mean? That simply means parts per 100 parts. Out of 100 total parts, some amount is ratio to the total amount. Now that could be, it could be grams per 100 grams, right? And that would be the case here, mass percent. And we designate that percent by mass or mass, right? 100 grams for the total, so many grams for the solute. That would be mass percent. And we get to that value by taking the mass or the grams of the solute and dividing by grams total times 100. Okay, that's mass percent. Now, this total is equal to grams of solute plus grams of solvent. If there is just one solute that we're interested in and the total, because this total, if there's more than one solute, which is possible, then we have to also include here the other solutes. This one is that solute. But if we have more than one solute, it has to be included also in the total. All right, that's mass percent. Now, what's the advantage of mass percent, right? If you specify what this percent means, mass, then you have a valid expression of concentration, and it is impervious to temperature changes, right? Mass is not going to change if the temperature changes. It will not change. Now, the solubility, of course, will change, but the value that you assign or that you determine from your mixture will not change because mass does not change with temperature. Okay? What's the percent by mass concentration of glucose in a solution where you have 5.5 grams of glucose and 78.2 grams of water? 5.5 grams, 5.5 grams plus 78.2 grams, right? You have to find the mass of the solute is also in the total times 100. And let's see, did I work it out? Yeah, 6.6%. But we should also specify mass, glucose, and what else is missing? What's the solvent? The solvent is water. So this is a complete, accurate expression of the concentration, mass percent of glucose in water from our problem. This way, there's no mistaking the character, various characteristics of the solution, right? It was formed by mass of solute per total mass of the glucose solute, and the solvent is water. Another common way of expressing concentration that's very useful for stoichiometric calculations is molarity. Molarity is given the symbol capital M, right? And it's a capital M for, well, a number of reasons. One is it's the first letter in the name, but it's also, it cannot be mistaken for any element because there are no elements in the periodic table that are simply one M, right? There are others like Mn is manganese, or let's see, Mg is magnesium, right? We can't, there's no mistaking a single capital M for any of the elements. All right, the expression here is in moles. Moles of solute per liter of solution. Okay, that's the definition of molarity. The advantage to this is if you have a solution of known concentration in molar terms and molarity terms, and you have 1 liter of that solution, you know that you possess exactly that many moles of solute. All right, 3 molar hydrochloric acid. It should be written this way: 3M HCl aqueous. That would be 3 molar hydrochloric acid. And in this case, it was the solution was made with 6 moles of hydrogen chloride in a total of 2 liters of solution. Now, how do you do that? Right? Because if you add 2 liters of water to 6 moles of hydrogen chloride, you may not have a final volume of 2 liters. Right? That's one of the disadvantages. When you're making a solution, you have to know what the final volume is. No matter what you put into it, the final volume must be accurately determined. And for that, we use volumetric glassware that's very accurately calibrated to a given volume. 2 liters, I used to work with a 2 liter volumetric flask day in and day out. They're shaped like this, have a long neck on them, and then a big bulb down here. Right? And this glassware is marked on the neck. It's usually scratched and etching all the way around. That shows you where the 2 liter mark is. Now, why do they put it on the neck? Why don't they put it down here somewhere? Because as you fill it up, you narrow the neck, then the volume, you add volume to it, it shows a greater change in length with a narrower neck. So this is where the volumetric mark is made. Okay, all right, how do you get your solution made in that situation? Well, instead of putting hydrogen chloride in there, let's say sodium chloride, right? So we're going to put sodium chloride in here, right? And let's say we put enough mass of sodium chloride there to give us 2 moles. right? We'll talk about how to do that in a minute. And you would have it here, you have a little bit of water, and then it dissolves in that water. And you get it in solution, and then you start adding more water. And you mix until you get to somewhere down here. Okay? Now, why did I stop there? I stopped there because most of the time, when you add a solute to a solvent, you get a temperature change. It's called the heat of solution. Sometimes it makes the temperature of the solution go down, sometimes it makes it go up. This is calibrated for a given temperature, usually 25 degrees Celsius. So, if it makes it colder, this volume is going to shrink. And if you fill it up to that mark when it's cold, then when it heats up to room temperature, you're going to be past the mark, right? And then I think the technical term is you're screwed, right? Your solution is unrecoverable. Now, if it heats up during solution and you bring it to that mark, then as it cools, it's going to shrink, right? So you're okay there. But to be safe, we just bring it up to this mark and then let it come to room temperature. And then once it's room temperature, with just a small amount of volume left, we add enough volume to bring it to the mark. And then we cap the top somehow and invert and mix. Invert and mix, get a thorough mixture. Now we have 2 moles of sodium chloride in 2 liters of solution. That is a 1 molar aqueous solution of sodium chloride. All right. That's how you do it. All right, another calculation. And the units of measure here are important. In order to do that calculation, the units have to be in moles of solute and liters of solution. So in this case, if we put 1 mole of sugar, let's see, 3 significant figures, 1 mole of sucrose in a final volume of 125 milliliters, we can't do the calculation yet. We have to know how many liters is 125 milliliters, right? If you work with this day in and day out, you know how to do that. I mean, just move the decimal 3 places. But if you don't, then we would say something like this: 125 milliliters. And we need to convert that to liters, right? So liters has to be on top, milliliters on the bottom, so that they will cancel. What's the relationship between liters and milliliters? Well, there's 1,000 milliliters in 1 liter. So we divide 1,000 into 125. And the way you do that is you move the decimal to the left 3 places. Okay, now we can put that in here, 125 liters. And divide 0.125 into 1. And that gives us an 8 molar solution. 8 molar, what was it? Sugar. Aqueous sucrose. Okay? All right. Let's make the problem more difficult. We looked at units of measure for the denominator, right, in our calculation. Now, how about the units of measure for the numerator? 500 grams of potassium phosphate. That can't go in the expression. That's mass, that's not moles. So 500 grams of potassium phosphate. Okay, here we're driving home the point. Early on in the semester, I cautioned you about learning how to write compounds from their names. If you never learned how to do that, then this is one of those places where you're going to fall flat on your face. Potassium phosphate. There's potassium. And there is phosphate. With a 3- charge, potassium has a 1+ charge because it's an alkali metal. This is an ionic compound, so all we have to do is balance the charge. 3 pluses, 3 minuses. So there's our formula. Now, how do we change 500 grams to moles? We have 500 grams, and we need grams on the bottom, moles on the top. Whenever you have grams and moles in a quotient relationship, think molar mass. So what's the molar mass of that compound? It's 3 times potassium, 3910 grams per mole. And we got 3 moles. And then phosphorus is 3097. Right? And oxygen is 16. Okay. So now we can calculate the molar mass of that compound because we wrote it correctly. All right, let's see. This is equal to 117.30. Yep. This one, of course, is going to be 3997. And this is going to be 4 times 16 is 64. And we can add those together. And 64. This is going to be 212.27 grams per mole. Okay, now we can convert this into moles. And I get 2.355 moles. Now we can calculate the molarity. Right? 2.355 moles per how many liters? 1.50. Now, as a practical matter, I don't know of any volumetric glassware that's calibrated for 1.5 liters. So this is a theoretical problem. All right, divide that value by 1.5, and I get 1.57. Let's see, what are we limited to? We're limited to 3 significant figures. So 1.57 molar potassium phosphate in aqueous solution. Okay. This is a more common type of calculation because, because we don't have any balances that will measure in moles, measure in mass, in grams. Another thing I want to emphasize here is this. Sometimes I abbreviate moles as a little n. Right? Now, a little n with a 0 up here, that's a neutron. So I don't want that. That means moles. And this is volume. But the volume has to be in liters. What we have here is a formula, right? We have equals M. So we have three variables. If we know two of them, then we can calculate the other one. That means if we already know the molarity and we know the volume that we're going to take out of that stock, then we can calculate the amount of moles of that solute that we have. Or if we want a certain number of moles and we know the molarity, we can calculate the volume that we need to extract to have that many moles of the solute. So here's an example. Let's make some room. Okay, you have a 10 molar sugar solution. That's given. What volume of this solution do you need to have 2 moles of sugar? Right? So if we look at this equation, the unknown is volume. So let's solve this equation for volume. Move V over here and M over there. Right? That's algebra. Just move the V over here, move M over there. Now, how many moles do we want? We want 2 moles. Right? And we have a 10 molar solution. Yeah, 10 molar. Well, what does moles mean? What does molarity mean? It means moles per liter. Right? Moles per liter. So numerator, denominator cancels. And denominator of the denominator is a numerator. So this liter flips up here and we get 1/5 liters or 0.20 liters. Let's see, 3 significant figures. 0.200. All right. Now, most glassware is not calibrated for liters. It's usually in milliliters. So how many milliliters would that be? Well, if 1,000 milliliters in a liter, then 0.2 of 1,000 is what? It's 200 milliliters. All right. Remember, as the unit of measure gets smaller, the number gets bigger. So that'll help you move your decimal in the right direction. You wouldn't move it this way because liter is getting smaller. This number has to get bigger. We go 1, 2, 3 positions. Ones, tens, thousands. I say tens, hundreds, thousands, excuse me. All right, how about this one? What we're trying to illustrate with this exercise is that even though you have the same mass of compounds, you won't have the same molarity because of molar mass. So 100 grams of sodium hydroxide versus 100 grams of potassium chloride in 250 milliliter of solution gives you a different calculation for molarity. So let's put sodium hydroxide over here. Right? And potassium chloride over here. And let's calculate the number of moles first. So if we have 100 grams here, we need a conversion factor that will give us moles. Right? So the molar mass of sodium hydroxide is, sodium is 23, oxygen is 16, and 1.01 for hydrogen. So that's 40.01. Divided into 100. That's 2.499 moles. Potassium chloride will be different. Right? Potassium is 39.1. And chlorine is 35.45. So that's 74.55. 74.55 into 100. And that's 1.341 moles. Okay. So now you can see that the molarity is going to be different because it's the same volume. So the molarity of sodium hydroxide is going to be 2.499 moles per how many liters? 250 milliliters is 0.250 liters. And that's 9.998 molar. And for potassium chloride, we have 1.341 moles per same volume, liters. So let's divide that by 0.25. And that's 5.3655. And rounded off. 4 significant figures. So you can see we have different molarities, even though we have the same mass of each solute. Rounded off 10 for sodium hydroxide. And it's just a little more than half for the potassium chloride. All right. You have 2 hydrogen chloride solutions. If it's aqueous, that's hydrochloric acid. Solution A and solution B. Solution A has a greater concentration than solution B. Which of the following statements is true? So let's say the molarity of, the molarity of A is greater than the molarity of B. If you have equal volumes of both solutions, solution B must contain more moles. All right, so let's break this down into the what this means. This is moles of A per volume or liter. Let's say liter. This is moles of B per liter. Okay? If you have equal volumes of both solutions, so these are equal, what must be true? If these are equal, then this one has to be greater than that one. Right? Solution B contains more moles than hydrochloric acid. That's false. Right? That's false. How about the second one? If you have equal moles of HCl in both solutions, solution B must have a greater volume. If you have equal moles, then this one volume must be less than this one, right? If you make the denominator smaller, then the quotient becomes bigger. So if these both are equal, then this one must be smaller than that one. B says solution B must have a greater volume. Yes, B is true. To obtain equal concentrations of both solutions, you add a certain amount of water to B. If it's already less concentration, you add more solvent, you get a less concentration. And it's still less than A, so that one's false. And D, adding more moles of HCl to both solutions will make them less concentrated. No, for the same volume, you add more solute, you get a greater concentration. So B is the only true statement out of those four. All right. Now, I mentioned this a little earlier. Not in this context, though. When you put sodium chloride in solution, if you put 1 mole of sodium chloride in solution, that yields 2 moles of ions. All right. So for concentration, if you have a 0.25 molar calcium chloride solution, you actually have 3 times that much in terms of ions. You have 0.25 molar calcium, but you have 0.5 molar chloride. And this is true, of course, only if the solute is completely soluble. All right. All right. So take this problem, and we want to know which one contains the greatest number of ions. So if we're counting numbers, we can count them in moles. Moles is a counting number. So 400 milliliters, let's say A, B, C, and D. So the top one is 400 milliliters of 0.1 molar sodium chloride. 0.1 molar sodium chloride. Okay. The next one, 300, 200, 800. 300, 200, and 800 milliliters. Okay. And then we have 0.10 molar calcium chloride and iron 3 chloride. And then sucrose. All right, let's look at the question again. Which one has the greatest number of ions? Sucrose does not ionize in solution. So we don't have to even bother with that one. It doesn't make ions. All right. So look at what we've got up here. If moles divided by liters equals molarity, then if we want to know the number of moles, we take this D over here. Number of moles equals molarity times volume. Okay? Now, we can convert this to liters, right? 0.4 times 0.1. But we don't have to, right? If we're only looking at the numbers of ions. If we multiply milliliters times molarity, we get millimoles. So this would be 40 millimoles of sodium chloride, right? If we have that many millimoles of sodium chloride, and how many millimoles of ions do we have? For every 1 millimole of sodium chloride, we get 2 millimoles of ions, right? Which equals 80 millimoles of ions. Okay. Now, I want to prove to you that this works. Right? If we have millimoles of solute, right, and we divide by milliliters of solution, right, millis cancel. So we still have moles per liter equals molarity. Okay, so there you go. This is a valid calculation. So 300 times 0.1 equals 30 millimoles of calcium chloride, right? Times 3:1 ions per millimoles, which is equal to 90 millimoles of ions. And the bottom one, 0.1 times that is 20 millimoles of iron 3 chloride. And how many? We have 1 plus 3 is 4. So here the ratio is 4:1. And 4 times 20 is 8. All right. So the one that has the most is B. All right. This is what I call my Henry Ford method, the assembly line. Each calculation is the same stepwise. We just change the values to reflect the particular problem that it's solving. So we do the same calculation over and over again. But instead of putting black doors on the Model T, we put white doors on the Model T. Okay, this is just an expression of problem solving, right? Where are you going, right? When you read a problem, I prefer, what's the question? What is the question that you're trying to answer? Then how do you get there? You devise a stepwise method for solving the problem to get to the answer. Right? And then once you get to the answer, does it make sense? All right. What's a standard solution? A standard solution is essentially what we've been talking about up to this point. We've been assuming that we could make a solution that was perfect. But a standard solution is guaranteed to give you a known concentration, known very accurately. Oops.
Hi, I'm Jared Hyman, an assistant professor of chemistry at Elon University. Today, I'll be taking you through the appropriate technique and procedure for preparing a chemical solution. One of the most important abilities at all levels of chemistry is the preparing of a solution of a specific concentration. First, we'll define some of the terms used in this process. A solution is a homogeneous mixture of 2 or more chemicals. For the simplest solution, a smaller amount of one chemical, called the solute, is placed in a larger amount of a second chemical, known as the solvent. Today, we will be preparing a solution of sodium chloride, using a small amount of sodium chloride as our solute, added to a larger volume of water, our solvent. Before beginning any experiment, it's important to observe appropriate lab safety procedure and know the hazards of any chemicals you're working with. In any chemical reaction, It's important to keep track of the exact amount of reactants present, and for stoichiometric purposes, we use the term mole to define the amount of a substance. A mole is a counting term, similar to a dozen eggs, where 1 mole is equal to 6.022 times 10 to the 23rd things. As you can see, this is a really large number. The periodic table uses molar counting as a means of converting to a more experimental term of mass. For example, 1 mole of carbon atoms has a mass of 12.01 grams. In a compound such as sodium chloride, it's made up of 1 mole of sodium atoms with a mass of 22.98 grams per mole, along with 1 mole of chlorine atoms with a mass of 35.45 grams per mole, giving us a total of 58.43 grams per mole of sodium chloride. This means of using mass to determine the amount of a substance is useful for pure chemicals. But in the case of solutions, we now have a mixture of multiple different substances. Therefore, we express amount as a concentration. The most common unit for concentration in chemistry is molarity, abbreviated capital M, which indicates the number of moles of solute dissolved in a certain volume of the total solution. This gives molarity derived units of moles per liter. It is very important to note that this is a volume of solution, not the volume of solvent. Today, we will be preparing 500 milliliters of a 0.25 molar sodium chloride solution. Before beginning, it's important to map out your procedure for preparing this solution. Here, we'll look at the amount of sodium chloride we need in this solution. We know that we want to prepare a 0.25 molar solution, which means that there is 0.25 moles per liter of solution. We also know that we only want 500 milliliters of this solution, or a half liter. If we multiply these two terms together, we can see that we will need 0.125 moles of sodium chloride. From earlier, we can remember that there are 58.43 grams per mole of sodium chloride. We can determine that the exact mass that must be measured out is 7.304 grams of sodium chloride. In lab, obtain some sodium chloride in a clean lab scoop, and using a balance with some weighing paper, measure out as close to 7.304 grams as possible, marking down your exact mass. Note that if you go over the desired mass, it's never appropriate laboratory procedure to put the excess reagent back into the original container. Always use an additional container to collect the excess. Once you've measured out your solid and recorded the exact mass, transfer all of the solid to the appropriate sized volumetric flask. Volumetric flasks are made specifically for this purpose and should be used over other less accurate labware, such as beakers, Erlenmeyer flasks, or graduated cylinders. Here, we just transferred our solute to the 500 milliliter volumetric flask. If any solute remains on the weighing paper, use a spatula or a small amount of water to transfer the remaining salt. Next, add enough water so that the bulb area at the bottom of the flask is approximately half full. This will give you enough room to swirl the liquid, allowing the solute to completely dissolve. Again, it's critical that all of the solute is dissolved prior to filling to the appropriate volume, as different solutes may take up more volume in solution than their undissolved salts. Now that the sodium chloride is completely dissolved, we can fill the rest of the bulb area and some of the neck with water. You should now carefully and slowly add water, our solvent, as it begins to fill the neck. Once you approach the etched or printed line on the neck of the flask, you should add solvent dropwise, monitoring the location of the meniscus. Water, as a polar solvent, tends to cling to the glass walls of a flask. This phenomenon creates what is called a meniscus. The bottom of this curved meniscus should sit directly level with the line on the flask. At this point, there is exactly 500 milliliters of solution with an air of 0.2 milliliters. Different volume flasks have different air values. However, the air on a volumetric flask is much lower than any other type of glassware of similar volume. For example, The volume markings on a beaker or an Erlenmeyer flask are only accurate to plus or minus 5%, meaning if the meniscus were on the 500 milliliter line, it could be anywhere between 475 milliliters and 525 milliliters. On the other hand, using a volumetric flask, we know that the volume is exactly somewhere between 499.8 milliliters and 500.2 milliliters, meaning it's much more accurate. We now must determine the exact concentration of our solution by taking the mass that we measured out and dividing by formula mass for sodium chloride, 58.43 grams per mole, which gives us a total number of moles in our solution of 0.1253 moles. We can then take this number and divide by our volume of 0.5000 liters to give us a total exact concentration of this solution of 0.2501 molar sodium chloride. This value and the contents of the solution should be clearly labeled on the chosen storage container for laboratory safety protocol. You've now learned how to make a solution from a solid. Everything you need to do this demonstration in your lab is available from Carolina. We have experts who can assist you with any of your science demonstration needs. Visit us at carolinachemistry.com to see our complete line of products and kits for chemistry.
All right. In order to make a standard solution, you have to know both very accurately the amount, the moles of your solute, and the final volume. The final volume we talked about in terms of volumetric glassware. For a solid, you would use mass and a balance with 3 or 4 decimal places. And that would generate a standard solution. All right. And we take into account the fact that most solutions either get cold or hot. So we don't fill all the way up to the mark until the solution, the partially made solution, reaches room temperature. Then we finish it off. Things that could go wrong, you could make an error in weighing the sample and weighing the solid, or in transferring the solid. Could spill some. You have to be sure that the solid completely dissolves. You could misread the mark on the neck, right here. Right? If your solution is down here and your eyeball is up here, then your line of sight is going to make you think that the solution is on the mark, but it's not. The only way to be sure is to have your eye over here. Right? Parallel with the mark. This error is called parallax error. Go look it up. Right? If we do have a very exothermic or an endothermic reaction, solution heat, then you have the potential for biasing your volume. All right. When I worked in soil testing, we had to extract elements from soils to determine their fertility, and we would analyze hundreds of samples a day. So we would need lots of solution. But to make up the solution every day would take an hour or two. So what we'd do is we'd make up a concentrated stock solution. And then at the beginning of the day, all we would have to do is take an aliquot of that stock and dilute it to a known volume, and we would have our working solution ready to go. So how does that work? How does dilution work? Well, the principal idea here is that when you have a stock solution of a known concentration, right, the concentrated version, and you take an aliquot out of that of a known volume, right, molarity times volume equals moles. So you're actually pulling out so many moles of the solute when you take that volume out. Then you put it into a known volume, your volumetric flask here. You put that in here, right? Now we call it N sub D for dilute. Did we change the number of moles? No, we just gave it a different variable. So N sub C equals N sub D. Those values are the same. They did not change. All right. So what does that look like in terms of its equivalence? Well, this one is molarity of the concentrated times the volume of the concentrated. This one equals the molarity of the dilute times the volume of the dilute. Right? So if this is a 1 liter flask, that would be 1 liter. If we took out 10 milliliters of the stock, that would be 10 milliliters. And then whatever the concentration is here, and this is the molarity that is our target. So that's why we can do a dilution. Sometimes you'll see it this way. M1 V1 equals M2 V2. Either way, as long as you keep your M's straight and your volumes straight. I'm afraid that was not going to work either because I think it's the same.
Hi, I'm Jared Hyman, an assistant professor of chemistry at Elon University. Today I'll be taking you through the appropriate procedure and technique for diluting a solution. A common laboratory technique is preparing a more dilute solution from a concentrated stock solution. In this case, we are going to prepare a 0.250 liter solution of 0.01 molar. We know our stock solution has a concentration of 0.250 molar. The first thing we need to do is determine the exact number of moles in our dilute solution. We know our concentration needs to be 0.01 molar or 0.01 moles per liter. Since we know our number of moles per liter and we know the volume we need, we can calculate that we need exactly 0.0025 moles of sodium chloride. Knowing our stock solution contains 0.25 moles per liter, we can take the number of moles needed in our dilute solution and divide by the concentration of our stock solution to calculate the exact number of milliliters that must be transferred into our new solution. In this case, 0.01 liters of sodium chloride solution, or 10 milliliters. This is the stock solution of sodium chloride that we will be diluting. Make sure to pour the stock solution into another container before inserting the pipette into the solution. This is because you do not want to contaminate your stock solution. In this case, I'm using an Erlenmeyer flask. Notice that I have clearly labeled the flasks to adhere to proper laboratory safety protocol. To prepare our dilute solution, we will take a 10 milliliter aliquot of our stock solution using a 10 milliliter volumetric pipette. To use the pipette, place the pipette in the liquid to be collected. Squeeze the pipette bulb and allow the liquid to rise up the pipette. You should allow the liquid to pass the line marked on the pipette, but before the bulb. Remove the bulb and place your other thumb over the end, creating a seal, and slowly release just the corner of your thumb, allowing the liquid to exit so that the meniscus is directly on the line marked on the pipette. This takes some practice, and you may need to use the bulb to pull more liquid into the pipette again. Never pipette by mouth. Once you have the exact amount of liquid required in the pipette, hold your thumb firmly over the end and transfer the pipette to a new volumetric flask. In this case, a clean 250 milliliter volumetric flask. Allow all of the liquid to flow out of the pipette. Do not use the bulb to force the liquid out, as pipettes are designed to deliver the exact amount of liquid, and there may be a small amount of liquid remaining at the end. Remove the pipette and follow the same procedure as before, filling the volumetric flask with solvent, again monitoring the meniscus until the exact volume is reached. You've now learned how to prepare a dilute solution from a stock solution. To see how to prepare a stock solution, you can view our solution preparation video at carolina.com/video. Everything you need to perform this technique in your lab is available from Carolina. Visit us at carolinachemistry.com to see our complete line of products and kits for chemistry.
All right. One piece of equipment that the presenter used that we hadn't talked about was a pipette, a volumetric pipette. It is calibrated to deliver a certain volume exactly. In that case, he was using a 10 milliliter volumetric pipette. And the calculation tells us that we need, solve for the unknown, that we need 0.01 liters or 10 milliliters. So that's why he used a 10 milliliter pipette. So that's the dilution technique. All right. I don't want to run out of time. Let me see how much time I got left. I'm going to need to move along. So next, a 0.5 molar solution of sodium chloride in an open beaker sits on a lab bench. Which of the following would decrease the concentration of the salt solution? Right? If it sits open on the bench, over time, the solvent is going to evaporate. But sodium chloride will not evaporate. It's not a volatile solid. So if we add water to the solution, that would decrease the concentration because we're adding solvent. Yes, A would work. Pour some of the solution down the drain. What does that do? It pours, you are removing the same amount of, a ratioed amount of solvent and solute. So you're not changing the concentration of what's left behind, right? That will not change. Add more sodium chloride would increase the concentration of the solute. Let the solution sit. Well, the solvent will be decreased and the relative amount of solute will increase. So the concentration will increase, right? And that one doesn't work either. All right. What's the minimum volume of 2 molar sodium hydroxide solution needed to make 150 milliliters of 0.0 molar sodium hydroxide solution? Okay, so this is a dilution problem. So for a dilution problem, remember, I've said this before, word problems, their primary objective is to confuse the reader, because we want to know if you understand the problem well enough to extract information from the problem and answer the question. So the way I do it is I take information from the problem and put it in an organized fashion. So the concentration, the concentrated molarity, the volume of the concentrated, the molarity of the dilute, and the volume of the dilute, since I recognize this as a dilution problem. Right? Then I put the numbers in their proper place. Well, what's the question? What's the minimum volume of the concentrated? Volume of the concentrated, that's the unknown. And the concentrated is 2 molar. We want to end up with 150 milliliters of dilute solution. And its concentration needs to be 0.800 molar. So now we have our values in the proper place. We can put them in the formula and we know that they're going to give us the right answer. So if we have this relationship and we solve for this one right here, then we can plug our numbers in, right? Notice that this is a ratio. So molarity is okay. We can use 150 milliliters. It doesn't matter. If we use 150 milliliters for the volume for the dilute, the units of measure for the concentrated is going to be in milliliters also. So we'll put the 0.8 molar volume of the dilute, 150 milliliters, divided by concentrated, 2 molar. And solve that problem for the unknown. We get 60 milliliters. So what does that mean? That means we take 60 milliliters of the concentrated solution and we put it in a device that will give us a final volume of 150 milliliters. Dilute it to the volume and mix it, and that gives us exactly 0.8 molar concentration of the solute in the final solution. Okay. We've solved problems of stoichiometry for mass relationships. We know how to do that. Now we're going to work on solving stoichiometric problems where volumes are involved, where our reactants are in solution. All right. And again, first thing you do is balance your equation. And then everything that is in terms of solution concentration and volumes, we convert that to moles. Because remember, you can't move anywhere in a balanced equation unless you have moles. So the same objective as our previous problems with masses, but now we get there by a different calculation. Then we may have to determine the limiting reactant. And then we continue working as always. Okay, here's a problem. We have 10 milliliters of 0.3 molar sodium phosphate, and we in one container, and we combine that with 20 milliliters of 0.2 molar lead 2 nitrate. Okay. So what precipitate will form? Well, let's write our compounds first. Sodium phosphate. Sodium and phosphate. This is a 3 minus. This is a +1. This has to be 3. And this is in aqueous solution. Okay. We're going to combine that with what? Lead 2 nitrate. Lead 2 nitrate. That means we need 2 of those. And that's aqueous solution also. All right, so what does that produce? I need to give myself some more room, don't I? Let's move it over here. Okay. Now, remember how we determine this is a double replacement reaction. This one replaces that one. So lead is going to react with phosphate. Three minus, 2 plus, cross multiply. So this one becomes 2, this one becomes 3. And then we look in our solubility chart and we find that lead 2 phosphate is insoluble. What's left over? We have sodium and nitrate. Which is soluble. Okay, so there's our equation with balanced compounds. We just need to balance the equation. The precipitate that forms is lead 2 phosphate. Okay. Lead 2 phosphate will form. So let's go back. Let's see. It's going to give it to us again. We're starting off with 10 milliliters of 0.3 molar here. So we have 10 milliliters of 0.30 molar. Okay. And we also have 20 milliliters of 0.2 molar. Okay. Okay, we found the precipitate that forms. Lead 2 phosphate. What's the mass of the precipitate that forms? We need a balanced equation first. So how do we balance that? Well, you can use your budget, right? And since we have nitrate here and nitrate there, phosphate there and phosphate there, we can use those as balancing units. But typically, the balancing of this type of equation is very simple. So if we need 3 sodiums on this side, I put 3 sodiums over here. Now we have 3 nitrates. We have, let's see. This is 2. That's not going to work because we got 2 here and we need 3. All right, back up. Try a different approach. Instead of focusing on sodium, let's focus on nitrate. All right, if we have 2 nitrates here, that's 2 sodiums, but we have 3 sodiums here. All right, so let's use the budget. I thought it was going to be easier than that. So we have sodium, phosphate, lead, and nitrate. Okay. We have 3 sodiums, 1 phosphate, 1 lead, 2 nitrates. And on this side, we have 3 leads down here. We have 2 phosphates down here. And we have 1 sodium and 1 nitrate. Okay. So let's focus on phosphates. We got 2 phosphates here. Let's make 2 here. All right. So that makes 2 phosphates and 6 sodiums. Now we want 6 sodiums on this side. Right? 6 sodiums here. That leaves 6 nitrates. Okay. Now we want 6 nitrates over here. So there are 2 there. That means 3 here. 6 nitrates and 3 leads. 6, 2, 3, and 6. Now we're balanced. Okay. I'm going to remove those. Yeah, there we go. Okay, we have a balanced equation. There we go. What's the limiting reactant? Well, we have absolute amounts of both reactants. So if we say use up all of this one how much product will we get? Right? So if we say, and I'm going to work in millimoles again. So volume times molarity is moles, or volume in milliliters times molarity is millimoles. So that is, let's see, 3 millimoles of sodium phosphate. We want to convert that now to lead 2 phosphate from sodium phosphate. The ratio is 2 of these, 1 of those. So that gives us half, 1.50 millimoles, oops, not milliliters, millimoles of lead 2 phosphate. Okay, we do the same thing with this one. That would give us 4, right? 4 millimoles. 4 millimoles. Yep. 4 millimoles of lead 2 nitrate. And then we want to convert that to lead 2 phosphate. So lead 2 nitrate to lead 2 phosphate. Ratio is 1 of these to 3 of those. So 3 into 4 is what? That's about 1 1/3. 1.33 millimoles of lead 2 phosphate. Okay. And there's the calculations using liters for volume instead. That's fine. So the limiting reactant is this one. And we've already calculated the amount of millimoles that we get from that reaction. Right? There we go. All right. So now that we know which one's limiting, we can use the outcome from that one. Now, we're going to have to change this to moles in order to do the calculation for mass. So 1.33 millimoles is how many moles? Well, look at that. That's milli, isn't it? Milli means 10 to the minus 3 moles. So this is lead 2 phosphate. There we go. Now we need to convert that moles to mass. So we need to know the molar mass of lead 2 phosphate, and it's given to us there. You just need 3 leads, 2 phosphoruses, and 8 oxygens, which is 811.54 grams. And that should be 1.08 grams. Okay? You have to be very methodical about these calculations. All right, so we've already got everything up here. The next question is, with this same experiment, what's the concentration of nitrate ions left in solution? The concentration of nitrate, the number of moles of nitrate in solution did not change, right? Because nitrate is soluble on this side and that side. So what we want to do now is, let's see, I'm going to erase this part and leave that stuff up there. How many moles of nitrate did we start with? Because that's the same amount that we end with, right? We had 4 millimoles of this compound, which means 2 nitrates for every one of these. So that's 8. We have 8 millimoles of nitrate ions. So what changed in this reaction? The volume. We had 10 mils here, 20 mils there. So the total volume is 30 milliliters. And like I proved to you before, millimoles divided by milliliters is molarity because the millis cancel. So 8 divided by 30, or 8 divided by 30 is and here we go, is 0.27 molar. Nitrate in aqueous solution. All right. And I say I got 10 minutes. I have enough time. I think so. One other question. What's the concentration of phosphate in solution? Phosphate did participate, right? So we started off with 1 phosphate for every mole of compound. So this 3 millimoles of sodium phosphate is also 3 millimoles of phosphate. Right? This is 3 millimoles of phosphate ions. But we used some of them up. How much did we use? Well, we ended up over here using 1.33 millimoles to make this compound. But there are 2 of these for every one of those. So times 2 equals 2.66 millimoles of phosphate. Right. So that means we used up this many millimoles of phosphate used. Right? So that's 0.34 millimoles of phosphate in solution. So now that we know that, we just divide this 0.34 millimoles of phosphate by the 30 milliliters of volume. And I get, let's see, here we go. Right. .01 molar. Now let's see, I get 1.13 times 10 to the minus 2 molar. Right. And if we move 2 places to the left, that's 0.0113 molar. Okay? Close enough. All right. So another type of reaction that we can study that occurs in solution is called a neutralization or an acid-base reaction. This is the net ionic equation for every acid-base reaction. For instance, if we have hydrochloric acid, and we're going to react it with sodium hydroxide, which is a base, acid with a base, right? What do we get? Well, we get sodium chloride, right, in aqueous solution, plus water, correct? All right, so what's reacting here? Well, you've got a hydrogen and a hydroxyl reacting to make water. This is a hydrogen ion. The chloride here cancels, and the sodium here cancels. You're left with this hydrogen ion plus the hydroxyl ion yielding water. That's the net reaction for every acid-base reaction. Here's the rub. Some acids have more than one hydrogen, like sulfuric acid. Some bases have more than one hydroxyl. A sodium hydroxide has one, but calcium hydroxide would have two. Magnesium hydroxide would have three. Aluminum hydroxide would have, two. Two for calcium, two for magnesium, three hydroxides for aluminum hydroxide. So sometimes the best approach is to use just straightforward stoichiometry. Right? In this case, we're going to react sulfuric acid, right, in aqueous solution, plus sodium hydroxide in aqueous solution. And we know it's going to give us sodium sulfate. That's a 2 minus, it's a 1 plus, so this has to be a 2. And this is completely soluble plus water. Now we need to balance the equation, right? 2 sodiums we need here, and 2 hydrogens plus 2 hydroxyls means 2 water. Now that equation is balanced. All right. How many moles of sodium hydroxide would be required to react with 1 liter of 0.5 molar sulfuric acid? So 1 liter of 0.5 molar gives us what? It gives us 0.500 moles of sulfuric acid. And if we convert that to sodium hydroxide, just like we always do, the ratio is 2 to 1. So that's 1 mole of sodium hydroxide is required to react with a half a mole of sulfuric acid. So there's our balanced equation. There's the conversion. Now, why does it take 1 mole of sodium hydroxide? Because for every mole of sulfuric acid, you have 2 moles of hydrogen. Sodium hydroxide only has 1 mole of hydroxide, so we need twice as much sodium hydroxide to neutralize sulfuric acid. Now, here's a concept that's very useful if you do this type of work day in and day out. It's called the equivalent. So 1 equivalent of acid is the amount of acid that furnishes 1 mole of hydrogen ions. Okay. Or actually, 1 equivalent of base would be similarly the amount of base furnishing 1 mole of hydroxide. Right? So whatever the molar mass of sodium hydroxide is, let's see, it's 23 and 16 and 1.01. And that's let's see, 40.01 grams per mole is also, since only one hydroxide per mole, it's also 40.01 grams per equivalent. Okay. Sulfuric acid is 2.02 for the hydrogens, 32.07 for the sulfur, and 64 for the oxygens. So we have 9, 0, 6, 7, 8, 98.09. This is grams per mole of sulfuric acid. But each sulfuric acid produces 2 moles of hydrogen ions. So you only need half that mass to give you the same equivalent. So it would be, let's see, 49.45, right? Grams per equivalent for sulfuric acid. That's the mass in grams of one equivalent of an acid or base. Right, and this just illustrates what I showed you on the board. If the acid only produces 1 hydrogen per molecule, then the molar mass and the equivalent weight are exactly the same. If the acid produces 2 hydrogens per molecule for the acid-base reaction, then the equivalent weight is half of the molar mass. Now, when we put these things together in terms of concentration, we have another term called normality. Normality is simply, instead of moles per liter, equivalents per liter. Okay. The nice thing about that is, once you've determined the normal concentration, it doesn't matter what the acid or the base is, because you've taken that into account already. So in that case, we can say the equivalence of base equals the equivalence of acid. And that would be the normality of the base times the volume of the base equals the normality of acid times the volume of the acid. Right? Now, if both the acid and the base only have 1 proton or 1 hydroxyl, then you can substitute molarity here because it's going to be the same value anyway. All right, if, whoops, I'm a couple of minutes over. Yeah, this won't take long. If barium hydroxide is used as a base, how many equivalents of barium hydroxide are there in 4 moles? If you have 4 moles of the molecule, you have 8 moles or 8 equivalents. That's it. All right, so next time we meet, this is Tuesday. On Thursday, we'll do a review. And I've got a buffer built in. I had saved next Thursday as a buffer for the lecture, but since we're finished with the lecture, we'll go into the review next Thursday. The sooner we can get a review done, the sooner you can start working on problems with these types of calculations. All right, that's it for today.